the video solution for practice problem A that accompanies sample problem 7.8 that appears on page 295 of your textbook. We're asked to write some electron configurations for ions. All of these ions that we see in this problem are transition metal cations, and there's a principle that we'll need to keep in mind as we look at all of these examples. The principle, and it's stated at the top of page 295, says that D block atoms will lose electrons from the S-NS subshell first, and then the N-1 D subshell. So what this means is that they will lose electrons from the highest energy S subshell initially, and then will come back and take electrons away from the D subshell as necessary to form the cations that you see here. Our first exercise is cobalt with a charge of +3. So let's begin by looking at a neutral cobalt atom. This would have 27 electrons, and they would be arranged in the subshells 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d7. If we remove 3 of these electrons to obtain a charge of +3, the electrons that we're going to take away are the electrons in the 4s subshell. There would be 2 of them, and that would mean that we also need to remove 1 of these 3d electrons. This loss is going to leave us with 1s2, 2s2, 2p6, 3s2, 3p6, 3d6 as the electron configuration for the cobalt ion that has a charge of +3. In the next question, we examine copper with a charge of +2. We'll begin our solution by thinking about a neutral copper atom that contains 29 electrons arranged as 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, and 3d10. Now this electron configuration does not follow the normal pattern that we've discussed in class about electrons populating subshells. Ordinarily, we would expect the 4s to completely fill before we put any electrons in the 3d subshell. But copper happens to be an anomaly to our previously discussed pattern. Copper is actually specifically discussed on page 261 in chapter 6, and in the case of copper it is more stable to have the S subshell half filled and the D subshell completely filled. You're not required to memorize all of the anomalies that can occur with electron configurations, but we have to consider them as we look at this exercise. If we remove 2 of these electrons to obtain a charge of +2, the electrons that we remove would be the 4s, and we would remove 1 of those, and then 1 of the 3d electrons. This loss would leave us with the electron configuration 1s2, 2s2, 2p6, 3s2, 3p6, 3d9 for the copper +2 ion. Our final exercise asks us to think about silver with a charge of +1. Notice that silver and copper are in the same group on the periodic table. As we thought about copper in the previous question, we're going to have to use an anomalous electron configuration for silver as well. Neutral silver will have its electrons arranged as 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s1, 4d10. So here's the anomalous part of that electron configuration, and that looks very similar to copper in our previous exercise. In this case, since our charge is just +1, we only need to remove one electron, and that electron will be the 5s electron. That loss will leave us with 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, and then 4d10 as the electron configuration for the silver +1 ion. You can practice the electron configurations of other transition metals by completing more of the practice problems in this sample exercise. The answer to practice problem B is in the back of the chapter.